So first of all, we'll discuss about linear regression. Okay, so what is linear regression? Okay, where we can apply, how we can apply, and how we can measure the performances. Okay, and then once we measure the performances, we understand that the performance is poor. Okay, then how we can improve the performances. Okay, so once we improve the performances, how we can deploy into production. Okay, after that, how we can monitor and how we can make sure that everything is working fine. So that's what we're going to see. So last week we discussed about what is machine learning, right? Like if you want to predict anything, okay, for future, okay, then you can apply basically machine learning. In machine learning, there are multiple algorithms. Okay, let's start with linear regression. Okay, so now think about the real world. Okay, you want to predict this. So take a task. Okay, so we can take some task and then we'll try to predict something. So now you want to do a task. Okay, that task is basically, okay, in Bangalore. Okay, what about the salary to the IT people? Means what the salary if what could be the salary for the 1 year experience resources? And what could be the salary for the 2 year experiences? What could be the salary for 3 year experiences resources? Okay, so you don't have any data within you. Okay, so first of all, you have to collect the data. Okay, so how you collect the data? You'll go to the people or go to the website. Okay, you'll conduct a survey. Okay, you know there are multiple ways to collect the data. Let's assume that okay, you collected the data. Okay, the data is like this. Okay, number of experience. Okay, you collected number of experience and salary. Okay, so this is what your samples. Okay, so if it is 1 year experience, what is the salary? Okay, this is the second guy. Okay, maybe we can put ID as well. Sample from the first people, second, third, fourth, 5. Okay, and then you have so many experienced people like that. Okay, for everyone you have a salary. Let's take a very simple example. Okay, let's take very simple observation. Okay, so this is your observation. Finally, you collected the informations. You collected the samples. Okay, so you collected the samples from 10 people randomly. Okay, the input is number of experience and the output is salary. Okay, simple. Now you have to apply machine learning algorithm and then you have to predict it. Okay, for the future. Okay, so after that you create a model. Okay, that model will accept number of experiences and then it will predict the salary as simple as possible. Okay, so now how we can choose the algorithm. Okay, so in machine learning there are multiple algorithms. Okay, how we can choose the algorithm. Before that you have to predict this problem, whether this is a supervised problem, unsupervised problem, or reinforcement learning, or semi-supervised problem. Okay, it's very simple. Okay, you have the input as well as you have the output, so it should be a supervised problem. Okay, so this is a supervised learning. Okay, under supervised learning, there are again multiple algorithms. So how I can choose the right algorithm? Okay, you see the target. The target is continuous. It is not discrete. So it could be anything between infinity, means minus infinity to infinity. Okay, you cannot take the starting value and the ending value. Okay, so obviously, so this is a regression problem. Okay, so first of all, okay, we see the input, we see the output. So obviously it's a supervised problem. We understand that. So we have to apply supervised learning. Okay, under supervised learning, there are two things: classifications and then regression. Means classification in the sense, if the output is discrete, it should be a classification. If the output is continuous, then it should be a regression. And we have seen that the output is continuous because it can ranges from minus infinity to infinity. Then this is a regression problem. Okay, under regression, there are multiple algorithms: linear regression, support vector machine regressions. Okay, so there are multiple things. Okay, neural networks. So we'll use linear regression. Okay, this is the starting one. We'll start with linear regression. So very simple. Okay, so what we did, we first selected the task. Okay, I'm going to predict a salary of resources within Bangalore area. Okay, so I decided to collect the data for that. So using some method, as I said, like either by through survey or I'll directly go, whatever it is, or through informations. Okay, means you can use Glassdoor as well. Okay, now creating all those websites, and then you collected the informations. Okay, so in your you have collected 10 observations or 10 samples. Okay, so the input is number of experience and the output is salary. Okay, and then we have seen we do have both input as well as output, so it should be we come to a conclusion in such a way that this is supervised learning. Okay, and then we see the target means the output, and it is continuous, ranges from minus infinity to plus infinity. So we and then we come to a conclusion that okay, it's a regression problem. Under regression, we take a very simple and then or the very starting algorithm, we can say linear regression, we take that. Okay, so now we have to understand how linear regression works. Okay, so before that we just set the flow. Okay, I mean to say what is the flow and what is the workflow basically. Okay, so first of all you have to collect the data collection. So data collection is done, we have the data. Okay, the second thing is identify algorithm. We identified algorithm. Okay, the third thing is applied model. The fourth thing is evaluation. Okay, let's take it very simple. We already collected data. Okay, done. We already identified algorithms. That's also done. And then we have to apply the model. Okay, so under apply model, what are all the processes available? Okay, so what does mean by apply model? Okay, apply model in the sense, okay, I'll call something called function. Okay, I'll create something called function. Okay, so through algorithm, I'll create a function. Okay, that function is y hat is equal to weight into x plus bias. Okay, otherwise I can say that, let's put it like this. Okay, so the model, when you apply the model to this data, it will create a function. Okay, that function is nothing but this. Output is equal to sum w into input plus b. Okay, so this linear regression will create a function like this. Okay, and then we do evaluations. Okay, let's come there. Okay, so now we have a function like this, right? Okay, so now we calculate w, we calculate b, and we know the input. Okay, then obviously using this function we can predict the output as simple as possible. Okay, so what linear regression, any algorithm will do, okay, that will simply create a functions. Okay, we'll use that function and calculate the future outputs. That's the main agenda of any algorithms. So I think you get the point, right? Okay, so we collected the data, we identified the algorithm, and then we are going to apply the algorithm. Okay, after that we'll evaluate the function, this function. Okay, so how we evaluate, how we can evaluate, how we can apply a model, those are all the things we are going to see. So before that, okay, let us talk about linear regression. Okay, so what is linear regression? How we can do that? Okay, so first of all, linear regression or any algorithm split into three things. Okay, one is hypothesis, another is loss, and then gradient descent. Okay, so anyway, we are not going to discuss about gradient descent this week's session. Okay, but I'll tell you, not detailedly, but tell you what gradient descent is, because it's very important to understand gradient descent to understand linear regression completely. Okay, so what is hypothesis function? Okay, we have already seen hypothesis function. Okay, that's the function we are going to create. Okay, the hypothesis function. Okay, so hypothesis function is equal to, okay, you know that output. Okay, let me go for output simplicity into is equal to weight into input plus some bias. Okay, so okay, this is my hypothesis function. So otherwise I can simply write w transpose of Okay, let's not confuse. Let's derive like this. Okay, and then what is the loss? Okay, so loss in the sense, okay, how you can evaluate your model basically. Okay, you need to understand the loss, right? Okay, you have collected a data. Okay, and that data. Okay, so let's take this example. You have collected the data, okay, and then you have both input as well as output. Okay, generally what we used to do for evaluation, okay, when we get the data, we split the data for training as well as evaluation. Okay, what I'll do, I'll split this. I'll take the six data for I'll take the six data for training, and then I'll take the remaining data for evaluation, four data for evaluation. Because it's important to evaluate the model, right? To evaluate, basically what I'll do, first I create a hypothesis function using this. I take this training data, six training data, okay? Through that, I'll create a hypothesis function, okay? After that, I have to evaluate it, okay? So evaluation in the sense, okay, this row, okay, we'll declare this very mathematically, okay? So we call output equal to y hat into w into I is the input, which is x again, plus bias. Okay, this is the formal hypothesis function, right? Okay, so now understand that I come up with a hypothesis function. Okay, so my hypothesis function is 3 into x plus 1. This is my hypothesis function. Okay, so now what I'll do, I know the w is equal to 3, I know b which is equal to 1. Okay, I already know the value of x. Okay, so what I'll do, so how I create this, okay, I create it by using this six data. Okay, then I'll take this, the training the test data. Okay, I'll take the input value, number of experience, I'll substitute here, I'll calculate the y hat. Okay, like that I calculate 4 y hat, means one for the first test data. Like that, for 4 test data, I'll create 4 y hat. Okay, so now I know the actual y value. Okay, so here I know the actual y value. Okay, and I calculate the y hat value. So now what I can do, I can subtract the actual value with the predicted value, what I get, okay, using hypothesis function. Okay, I'll subtract that, and then I'll calculate the loss. Okay, if the loss is 0, means I predicted 10,000, the actual value is 10,000, then obviously the loss is 0. If the loss is 0, it's well and good, yeah. It's predicted exactly. Okay, it's 100% accuracy if the loss is 0. But if the loss is some high value, then I predicted very worst. It's not at all predicted good. Okay, for me, what I mean to say, okay, you subtract y minus y hat. Okay, your actual value is 10,000 and you predicted only 1,000. Okay, think about it. The loss is 9,000. Okay, so how you predict the accuracy? Let's not worry about accuracy right now. Okay, so through loss, you can understand this is very high value. So obviously your model is not at all good. The function is not at all good. So what you can do, you can re-evaluate, means you can retrain, and then you can try to decrease the loss. Okay, that's what we are going to do. That's what loss function. Okay, through loss function, okay, I can understand what is the loss. Okay, so loss is equal to y minus y hat whole square. Okay, and then we have to sum it as well. Okay, because here we have 4 values. Okay, first value will take the last one, last 2, last 3, last 4, and then we'll sum it finally. Okay, that is our total loss. Okay, and right now I'm not going to discuss about gradient descent. What gradient descent? I'll simply say maybe at the end of the class we'll discuss about gradient descent. Okay, because obviously you would have a chance to confuse if I explain gradient descent now. Okay, so right now this is the two things. One is hypothesis function, one is loss. What hypothesis function will do? You have a training data, and then you'll come up with a function like this. Okay, some people will say this function is universal function approximator. Okay, but anyway, there are a lot of deviation in that. Okay, some people call this, some people call universal function approximators only apply for neural network, but I can say, even for linear regression, you can say this function is universal function approximator, or simply function, or simply hypothesis function. Okay, so using training data, you'll calculate something called hypothesis function. Okay, so through hypothesis function, you can predict something using the input value. Okay, so now we predicted. Okay, but you have to evaluate a prediction. For that, you have to understand the loss. So for that, we'll come up with a loss function. Very simple. Okay, so if you see any algorithm in the world that has this two, hypothesis function and loss, because obviously we have to define a function. Okay, using that only we can predict output, and then we have to define loss, because we have to understand how the model is performing. For that we need to understand the loss. Okay, now let's take the simple example, this example. Okay, so I delete everything, I'll keep only function. Okay, so the hypothesis function is y hat is equal to w, which is weight, into x plus b. Okay, so we can write like our input. So we have only one x1. Okay, only one input variable, we call that as x1. Okay, so then w1 plus b1. Okay, so I take this as x1, I take this as y. Okay, I have only one input, so the hypothesis function can be written like this: x1 into w1 plus b1. Okay, so now how we can calculate this? Okay, so how we can do that? So you can assign w value initially. Okay, when you start, just assign initial value, assign w value, assign some random value, some 0.12. Okay, then apply this value to this formula. So now y hat is equal to 0.12 into x1 plus b1. Let's assign as 1. Okay, so during starting, no one will tell the value. Okay, so obviously we'll assign by ourselves randomly. So okay, we assign w1 is equal to 0.12, b1 is equal to 1. Okay, so now we got the complete function. Okay, so now I have this thing, right? What I'll do, okay, now I'll take this number of experience. Okay, I'll substitute here. Okay, y hat is equal to 0.12 into number of experiences 1 plus 1. So now I get y hat is equal to 0.12 plus 1, which is 1.12. Okay, so I take the first observation here. Okay, this observation. Okay, for this I know that target value means the y value. What is the y value? 10,000. Okay, now I know the loss function. Loss is y minus y hat, which is 10,000 minus 1.12. Okay, calculate the loss. Okay, then I come to know that the loss is high. Okay, so I have to increase this w value. Simple. Okay, so what I did, let's go through that. Okay, so we take the hypothesis function. Okay, so we come up with the formula x1 w1 plus b1. We assign w1 and b1 randomly. Okay, and then we take each and every training data. That's important. Okay, so I calculate this. Okay, for first observation, for first training data, the y hat is 1.2. For the second data, it should be 1.12. For third data, it should be 2.24, something like that. Okay, so I calculate y minus y hat for all 6 observations. Okay, so I'll get some value. I'll sum up. Okay, then I get the final loss. Okay, so I understand my loss is really high here. Then what I can do to decrease the loss, I can increase this w1 and b1 value. So from this value, what I'll do, I'll increase by 1, and then I'll increase by 1. I'll increase the weights or parameters by 1. I'll again apply this function. I'll get the loss. Okay, so again my loss is high. I'll again add weights plus 1, bias plus 1. Okay, this is the iterative process. Okay, so I'll do for first iteration, second iteration, third iteration until my loss is low. Okay, so let's assume that I did some 10,000 iterations. I come up with a function like this. So after 10,000 iteration, we got a function like this. Okay, now take the first observation. The number of experience is 1. The salary is 10,000. Means the predicted value is 10,000. So we'll take the number of experience. We'll substitute here. So 1 into 1 plus 10,000 is equal to 10,000. I'm sorry. The function shouldn't be like that. 10,000 into x1 plus bias 0. Okay. So after at the end of 10,000 iteration, I calculate a formula like this. Then I'll substitute. Okay, 10,000 into 1 is equal to 10,000. Okay, I got a y hat value. What is the actual value? Actual value is also 10,000. What is my loss? It is 0. So like that, I calculate for all training data. Now my loss is 0. So I get the 100% accuracy. I stop the training process. Okay, so then this is my hypothesis function. So this is what we do. Okay, so we define hypothesis function. We'll initialize W1 and B1 value. Okay, we'll get the loss. We'll see the loss is high or low. If it is high, we'll go to the second iteration. During the second iteration, we'll take the previous weights. We'll add it by some value. We'll increase that. Again, we'll assign those value to hypothesis function. Okay, and then we'll calculate the loss. This is an iteration process. After 10,000 iteration, I'll get the real value. Means when my loss is 0, I can understand that this is my real hypothesis function. Very simple, right? You know how we define the process. Okay, we take the input, we take the output, and then we define a hypothesis function. Okay, so in hypothesis function, we know one parameter, which is x. We don't know, we're not sure about other two parameters, w1 plus b1. Okay, so we initialize w1 and b1 to some value. We calculate the y hat. We know the actual value. We subtract it. We calculate the loss. Okay, and then we do multiple iteration to decrease the loss as simple as possible. This is how every algorithm in the market works. Not every algorithm, most of the algorithms. Okay, and I can say most of the discriminative algorithms work like that. Let's see what is discriminative, what is generative, what is probabilistic models. All those things we'll see that. But right now, don't confuse with that because we are in a very early stage. I guess this is because this is important, very important. That's why I explain very slowly. Okay, so don't ever forget this. Okay, so because this is what we're going to discuss in most of the sessions. Okay, so we take from linear regressions and then why linear. We'll try to understand why linear regression is not fit for this input. So how we can fine tune this algorithm. So this is what we're going to see. So this is important. So now let's open Jupyter Notebook. Okay, so Avi asked the question, do we need to calculate hypothesis for all time data? Yes, Avi, because it's important. Because then only you can understand, right? Because for example, you have 10,000 training data, but you calculate hypothesis function based on only 5,000 training data. Then it's the bias because you do have 10,000 training data, but you're calculating only for 5,000 training data. Then the hypothesis function will not reflect for 10,000. It will reflect only for 5,000. So then, because more and more training data, you can come up with more and more good hypothesis function. Okay, in machine learning, that's why people say if you have more data, you can come up with a very good hypothesis function because you see the formula how we did. Okay, so I'll skip this because I already explained this. So before that, I want to explain one more thing. Let's delete all this. Now we have experience and salary, right? Okay, some people will call as inputs, X as inputs, Y as outputs. Okay, our futures and target are independent variable and dependent variable. Okay, so if you go to deep learning world, people call this futures and target. In the layman example, in the layman way, we call that as input and output. In machine learning, we calculate this independent dependent variables. Okay, so there are multiple notations. Okay, so I can say, right now you can assume whatever you want. Okay, So, but we can assume features and target. Let us assume right now like this. Okay, but anything can be, you can see, either independent or dependent variable, whatever it is. Okay, so now let's define this. Okay, so now let's plot a graph. Okay, assume that this is the x1 value. Okay, the number of experience. This is the y value, which is the salary. Okay, and we collected some points. Okay, means when the number of experience is 1, the salary is 10,000. Okay, when the salary is 10,000 and the number of experience is 1, how many people do we have? I'm sorry. Okay, so let me use different colors. Okay, this is one of the observation. Okay, like that we collect multiple observations. Okay, that's our data, right? This is samples. Okay, so I collect multiple observations. Okay, this is my training, this is my sample basically. Okay, so what I do basically, I try to linearly separate this. For example, I'll try to linearly separate this by a straight line. Okay, so what I mean by, this is my observation, right? This is my number of features. This is my salary. Means, I'm sorry, the x1 is the number of experience and y is the salary. Okay, I got a observation. I got every samples. Okay, then I plotted it. Okay, so now let us forget everything. Let us forget the straight line. Okay, so how we can predict for future data? Okay, so now this is your data, right? This is your sample. Okay, so now you need to create a model. Okay, and that model should create a function, and through that function you need to calculate the future output. Means in future I can say that the number of experiences some 10 years you need to predict the salary. Okay, so for example, assume that this is a new feature, a new input. Okay, so now you came up with a model. Okay, I come up with new input. Okay, so how you can predict this? Okay, the number of experiences some 11 years. You have to predict the salary for this. What you can do, you can put a strike line here. Okay, what is the y value? Assume that the y value is 1 lakh. Okay, then you can predict like this. Okay, that's what you're going to do. Okay, so don't confuse a lot. What we're going to do, assume it in a plot. You have number of experience and you have salary. I have plotted it. Okay, then what I'll do generally, I'll come up with a hypothesis function. Okay, that hypothesis function is a straight line, because assume the formula of straight line. Okay, if you try to understand the formula of straight line, okay, can anyone tell what is the formula of straight line? Okay, the formula of straight line is y is equal to mx plus c. That's the formula of straight line, right? Okay, so what I do is separate this. Okay, and then I calculate the formula of straight line, because this is straight line. So the formula of straight lines is y is equal to mx plus c. M is the intercept. Sorry, m is the slope, c is the intercept. This is mathematical formula. Okay, so don't confuse with that. Okay, so now this is the straight line is my hypothesis function, and the straight line equation is y is equal to mx plus c. Now see our equation, that is y is equal to y hat is equal to wx plus b. Isn't it similar then? Okay, it is exactly similar. So this hypothesis, the straight line equation is nothing but a hypothesis equation. Okay, instead of m we put w, and instead of c we put b. This m is the slope. Okay, you know what? The slope is, anyway, I don't want to confuse a lot, but I'll try to understand what is slope. Okay, I'll try to give you the understanding. Okay, I want you to understand what is slope is. Okay, this nothing but slope. This is nothing but slope. Okay, to calculate slope, okay, so we'll take the y split and x split, and then we'll add it. We'll come up with the value of slope. Okay, so that's m. Okay, and c is the intercept, some constant. Okay, that's what we do here. Okay, so what we do, okay, so we have x-axis and y-axis. Okay, so we just pointed our observation. Okay, and we need to separate this. Okay, why we need to separate this? I'll tell you. To predict for future. For now, take an example. Okay, now some value comes in future. Okay, now with straight line, what you can generally do, just from this point, draw a straight line, okay, and see the value. That's your y hat value. Simple. That's a predicted value. And if the point is here, just create a straight line and hit that particular boundary, and then what's the value? To predict that. Okay, if it is up, then this is, then this is, then this is. Okay, so if you see that this is the real y value, okay, for this point, and if you draw a straight line, this is the y hat value. Okay, this is y, this is y hat, and this is the loss. The straight line, the blue straight line is the loss. Okay, so what we try to do, we try to decrease the distance between y and y hat. Okay, so every time what we do, okay, so first of all what we did, okay, we initialize w and b value and we fix some straight line. Okay, and then we'll see the loss and then we'll try to change the slope. Okay, so now the loss is heavy, so I'll try to change the slope. Okay, and then I'll try to change the slope again. Okay, so now we can see the distance is decreased. Okay, so like that only we do. Simple. Okay, so full of mathematical substitutions. Okay, so any doubts on this? You understand, right? Why we use a function, why we use the formula y is equal to mx plus c, where it comes from. It's a straight line formula. Okay, and then how the last function comes in. Okay, how we can predict the future. Means how we can predict the future value. You understand this concept, right? Because this is very important. Okay, I hope everyone understand this particular concept. Okay, so let us remind that again. Okay, so we'll walk through once again very fastly. Okay, so now we have to solve the linear regression problem. Okay, the linear regression would have input variable and output variable. Okay, so what I can do basically, I need to come up with a boundary like this. Okay, so I'll take a very easy boundary, which is straight line. Okay, the formula of straight line is equal to y is equal to mx plus c. Okay, I take the same formula and substitute as y hat is equal to wx plus b. Okay, this m is nothing but w, which is slope. The c is nothing but b, which is bias. Okay, so now what I try to do, okay, I'll calculate the y hat value. I'll already have the y value. Okay, I'll compare this. Then I'll get a loss. Okay, then based on the loss, I will decide whether I can go for a better straight line. Yes, I can, because the loss is too high. Then I'll increase this m value and c value. Then the formula gets changed. Then I'll get a new straight line. Okay, like that I'll come up with so many decision boundary, and then I'll stick with the decision boundary, which gives the best, a very small loss and very high accuracy. Very simple. Okay, that's what we are going to do. For that process, so obviously here we do multiple iteration, right? Okay, so first I started with some initial random value, then I increase that, like that. We have to do some 1,000 or 5,000 or 10,000 iteration if possible. Okay, and someone has to define the process. Okay, how I can mathematically iterate it. Okay, so one of the process is gradient descent. There are a lot many processes, but the one of the best process in the market is gradient descent. Okay, so but anyway, we'll discuss about gradient descent in later section. Okay, let's not worry about gradient descent right now. So now let's see examples. Okay, so through that we'll try to understand this concept again. Okay, this is what they explain in this first part. Okay, so now let me restart and clear all outputs of my Jupyter notebook. Okay, I have pandas and matplotlib. You know what pandas is. Okay, so that's basically get all the input as a data frame. Okay, and then I use matplotlib for plotting. Okay, and then I have some inputs. Okay, this is basically if you want to see the input, you can go to the website. Okay, this is we got from web. Okay, so we'll see that. Okay, so now I read a CSV file from the web. Okay, and I have it in this pandas object. Okay, called data. Okay, so now I'll try to fetch some values from this object data to understand how the value looks like. Okay, so now this is our input. So we have, so let's call it as futures and target. We have three futures. Okay, the TV1, radio, and the newspaper. This is the three futures, and the target is sales. Okay, so when I say futures and target, you can understand that, okay, using futures, we are going to predict the target for future. Simple. Okay, for that, we need to collect the data. The data is this. Okay, so this is very simple. Okay, how my sales is increasing. Okay, I'm basically advertising using TV, radio, and newspaper, which basically increase my sale. Okay, so which is more prone to pull the customer to purchase that particular product. Okay, so when I use a TV ad, okay, how my sales increases. When I use a radio ad, how my sales increases. When I use newspaper for an ad, how my sales increases. That's what we're going to predict. Okay, so in future, okay, so I'll create a hypothesis function. In future, what customer do? Okay, I'll invest some this much amount in TV ad. How much sales I'll get? Okay, if you want to predict that, obviously he can use linear regression. That's what we're going to predict. So any doubts on this problem? Okay, what we're going to do? Very simple. We have futures and target. Okay, the futures are TV, radio, and newspaper. The target is sales. Okay, for future, if the customer want to know, okay, if I spend this much amount in TV, this much amount in radio, this much amount in newspaper for an ad, then how much sales I'll get. Okay, so I understand that radio, newspaper, people are not through this formula. Okay, through this formula, I can understand that even though if I increase the radio and newspaper ad, my sales is not increasing. But if I increase the amount in TV ad, my sales is increasing. Okay, so all this intuition will give the hypothesis function. Okay, so right now, don't think all this. We collected futures and target. The futures are TV, radio, and newspapers, and the target is sales. Okay, and then you can put data.shape, okay, which is row and columns. So I have 200 rows and 4 columns, means okay, till 200, and then 4 columns. You know that what 4 columns is. Okay, TV, radio, newspapers, and sales. These are 4 columns. Okay, means this is my sample. I have collected 200 samples and a 4 different categories. Okay, so using data.shape, you can understand this. Okay, so then I'm going to plot this. What I'm going to plot? The scatter plot. We already discussed, right? In the x-axis, we have number of experience. In the y-axis, we have salary. Like that, since we have 3 features, TV, radio, and newspapers, and the target is sales, I'm going to create 3 plots, okay, that will tell me, okay, how the input and output is behaving. Is basically how the behavior is. Okay, so I'm going to create a plot in a matplot. Okay, I'm going to create subplots. Okay, the subplot consists 1 rows and 3 columns. In a single row, I have 3 plots. Okay, so the kind of plot is scatter. Okay, the x-axis is CV, y-axis is sales. Okay, so and then figure sizes. Okay, so this is the axis 1, means axis 1, 2, and 3. Okay, so when you execute this, okay, we got an error. Let's see that. Okay, it's basically small letter. Okay, so I used recent pandas version. It is not taking this. Okay, let's see a recent most example, and then we can change it accordingly. Let me remove this. I think something is missing here. Yeah, okay, got it correct only. So the problem with the very value. So if you see that, it's actually small. It's lower cases. Okay. So when you just change that, okay, then it provides three plots. Okay. So the first plot is against TV versus sales, radio versus sales, newspaper versus sales. So frankly speaking, when you see that, obviously we couldn't get any intuition. But we can say that, this is kind of linear. Okay. If you just cycle for this, you can come up with a predictions. Just think about it. And like if you just fit a strike line from here to here, it's kind of predictable. Okay, so we can say that it is basically a linear kind of thing, not a non-linear. Okay, we'll discuss about what is linear, what is non-linear. Okay, so maybe yeah. Okay, okay, that's important. So we'll discuss that also. Okay, when I say linear, it's basically predictable. Means okay, I plot a linear data. Okay, the linear data is like this, normal distributions. Okay, but what nonlinear data is, it will be chunk. This is nonlinear. Okay, if you see the data, if you plot each and everything, okay, and then if you just draw a line on the data points, then basically you'll get a function like this. That is nonlinear function. Okay, the linear function is this. Right now, we are assuming everything we got, okay, everything are linear. Okay, so we're not, we'll talk about nonlinear, okay, later. But right now, everything is linear. Okay, see now, these are all some simple linear regressions. Okay, we have discussed all this. Okay, now it comes to scikit-learn. Okay, so and one more thing. Okay, okay. So right now we know what things as we have fixed. Okay, so we have W and B, weights and biases. Okay, some people call this as coefficients. Okay. Okay, very simple. So you have to understand this notations. Okay, so we have X, we call some people, so you can call it as inputs or features or independent variables. And then this is Y, outputs target different variable, and this is weights, coefficients, or biases. Okay, so using this variable, we build a hypothesis function. Okay, and then this is the y hat value. We already know means we predict the y hat value. We already know the actual value y. We calculate the last function. Okay, as we already discussed, we have seen some packages in Python, right? Okay, so first of all, okay, let me define that. Okay, so in the first half of the session, we have discussed all the basics things. What is hypothesis, what is last, what is gradient descent, what is B, what is W, what is X and Y, what is Y hat, and all those things. Okay, how we can evaluate. Okay, so, but obviously we cannot write all this logic in hand because this is very big. And obviously, we have to find some nice packages who can do all this kind of things for us. Okay, so we already discussed pandas, we already discussed matplotlib, we already discussed about numpy. Okay, we have seen some of the packages, right? So like that, there are one nice package for apply machine learning algorithms. Okay, that is nothing but scikit-learn, sklearn. Okay, this is one of very popular library in Python community, particularly in data science community, and it uses NumPy as well as SciPy. Okay, in the backend. So obviously, you can use, this is a good combination. Okay, pandas, matplotlib, NumPy, and scikit-learn is a good combination. So using that, you can create any kind of machine learning algorithms. Okay, it has wide range of varieties of algorithms. Okay, we'll see one by one anyway. Okay, so now how I can apply scikit-learn. Okay, so scikit-learn provides so many algorithms. Okay, so you can go to scikit-learn. Okay, and then you can import linear regressions. Okay, if it's a logistic regression, you can say logistic regression. If it is a support machine, you can say SPM. Okay, then you call linear regressions. You call this object. Okay, then you'll fit it. Okay, that is the training process. Okay, so you have to come up with a hypothesis function, right? Okay, when you fit, you can come up with a hypothesis function. Okay, the single method. Okay, so this is an object, linear regression. Okay, and then you call this object with a method called fit. Okay, this single method will done with all the training process. Okay, it calculates a hypothesis function. Okay, to calculate hypothesis function, what you basically need x and y. Okay, so what you basically do, you'll come up with x value and y value. Okay, and then you'll fit it. Means you'll calculate the hypothesis function. Okay, so here is the form. Here is the here we get the x and y value. Okay, so we have stored all our data into a variable called data. Okay, so it has 4 columns in it. Means TV, newspaper, radio, and sales. Okay, right now I'm taking only one feature, TV. Okay, the future column is equal to TV, and the x equal to data of future column is TV. So that is x value. Okay, so x is nothing but the TV, y is nothing but the sales. Okay, so pandas, you can even try data of sales. Okay, or otherwise data dot sales, anything is fine. Okay, so now in the x we have TV, in the y we have sales. Okay, so we call scikit-learn, okay, linear regression, and then we instantiate this object, and then we call a method fit. Okay, we pass x and y value. Okay, and then what we are trying to get, intercept and coefficients. Okay, so what is intercept? The p value, the bias value is the intercept. Okay, and then the coefficient value is the w value. Simple. And when you execute this, it comes up with this. Okay, the intercept is 7 point something. Okay, so otherwise more formally we can write like that. Okay, so y hat is equal to w1 into x1 plus b1. Okay, so this is the function we have to come up with basically. Okay, so more generally we can write y hat is equal to, okay, w1 is the w1 value into x1 is tv plus b1. Okay, so now we have to calculate w1 and b1. Okay, so that's what we did here. Okay, so now the w1 value is 7 point something. I'm sorry, intercept is b1 and coefficient is the w1. So w1 is this. Okay, so we calculate b1 and w1. Let's rewrite this formula like this. Simple, we got a formula. Okay, we got the y hat formula. Then if you want to predict anything, you can use that. Okay, that is what the scikit-learn will do. Okay, I hope you're clear with this. Okay, simple. We extracted x and y from data, and then we apply linear regression. We called a model called fit, and then to print intercept, we call intercept. To print coefficient, we call coefficients. Okay, as simple as possible. Okay, so there's a very big method, but scikit-learn did this within 4 lines of statements. Okay, next, how we can predict it basically. Okay, so now assume that you are spending 50 for a TV advertisement. Okay, then what's the sales value? Simple. Okay, so now okay, in future, okay, I'm going to spend some $50 on TV advertisements. Okay, what is the expected sales? You can predict that, right? Okay, so using this you can predict anything. Okay, but you can ask, like, would scikit-learn provide any function to predict? Yes, it did. The function is predict. Okay, so you can call lm. Okay, lm is the object, lm.predict, and x of new. X of new is the new value. Okay, the 50, and then it predicts the output as 9.409. Okay, so in scikit-learn, it's very simple to understand. Okay, there's a class or object called linear regression. Under that, there are multiple methods. Okay, so we're trying to use this. Okay, the fit will create hypothesis function, and then predict. Okay, we'll try to predict the future predictions using input, and then evaluation will tell us the accuracy loss and everything. Okay, we'll see one by one. Okay, so now what we try to do, okay, we'll come up with a style. We earlier session we come up with a plot, right? Okay, in the scikit-learn itself, we'll try to come up with that kind of plot. So it it would be easy for understanding. So what we try to do, okay, we know data. Okay, so data that TV has minimum value and maximum value. We'll take that minimum value and maximum value of that. For example, in the TV, you have minimum value as 1 and then maximum value is. So now what we can do basically, what we're trying to do basically, we'll try to come up with the same the linear fit curve. Okay, so through that we try to understand. So that is what we're going to do in scikit-learn, how we can achieve. Okay, so for that, what I'm taking, okay, if I know the, this is x, right? So the x is nothing but TV. Okay, this is nothing but TV. So if I know the minimum value and the maximum value of x, and then a y, minimum value and maximum value of y, then I can basically get this point. I can get this point. They can create a straight line. That's the idea. Okay, so I'm trying to get the minimum and maximum value of x and minimum and maximum value of y, and then that's my coordinates. Okay, this is starting coordinates, this is the ending coordinates, then I'll plot a straight line. Okay, simple. So that's what I'm going to, that's what I'm trying to get. Okay, so I get the minimum and maximum value of x new. Okay, the minimum value is 0.7 and the maximum value is 296.4. Then I'll predict the y value for 0.7 and 296.4. Okay, I get 7.0 and 21. Okay, now I'll go with a scatter plot. Simple. Okay. So first I'll go with the scatter plot. This will give all this. Then I'll go with the plot of the X new and predictions. Okay, the line. You can see that. Okay. So this is a real data, and we come up with a line like this. Okay, this will separate. This is a decision boundary. This will tell us what could be the output, predicted output. Means, for example, if my new data point is here, okay, assume that if my new data point is here, then I can draw a straight line against this boundary. Okay, so then I'll take that end value. Okay, so do you guys have any questions? I think this is very clear, right? We already discussed that, and we're just trying to write everything in Python. How we can uh, you know develop by using Python. That's what we're seeing. Okay. So now, now we come into the evaluation process. Okay, so we identify the data. Okay, so we identify the problem, and then using scikit-learn, we apply a model. Okay, and then we calculate intercepts coefficients, and then we know how to predict it, how to get the intercept and coefficients, how to fit. We know everything in scikit-learn right now. Okay, so now how we can evaluate the model, how we can get the accuracy, how we can get the loss, how we can improve accuracy. All these things we'll see. Okay, so this would be a little difficult because this is mostly into statistics. Anyway, I'm not going to explain anything mathematically. Okay, let's see the concept first, and then we go one by one. Okay, so as a disclaimer, like this would be a little difficult, so please, just concentrate, a little bit. Okay, so what is the confidence interval? We have already seen when we see the statistics in normal distributions, we have seen the confidence interval. Okay, so for example, we have seen the intercept, right? Okay, so if you see the intercept or coefficients, okay, so we have that ranges from one value to another value. Okay, so for example, okay, so it takes W. Okay, this basically ranges from some value to some value. Okay, the minimum value is 0.1 and the maximum value is 0.9. So, but this is, okay, now the same thing, we'll plot it as a normal distribution. Okay, anyway, this could be a normal distribution. Okay, and we know that anything within 95%, that is good. Anything out of 95%, that is not good. That is kind of outliers. Okay, so that is what we're going to predict. Okay, so now we predict coefficients. Okay, so we need to understand whether that coefficients lie within the range of 95%. Okay, that is what we're going to see. Okay, so how we can get that? Okay, so what I'm doing, ordinary least square, which is nothing but the loss function. Okay, so what is the loss function? Just recall the loss function. Loss function is y minus y hat whole square, right? Okay, that is nothing but the ordinary least square. Okay, so ordinary least square is this. Okay, so now what I'll do, okay, so I'll take sales and TB. Okay, I'll fit hypothesis function. Okay, so we can see that I fit it. Okay, for this hypothesis function, I'll calculate the ordinary least square, which is loss function. Okay, so now my loss function is, assume that this is 1.25 or something like that. Okay, so now I come up with the loss function. Okay, so I know y hat. Okay, so calculate loss function through ordinary least square. Okay, so now I can calculate the confidence interval. For example, anyway, we're not going to see the formula, a little difficult. Okay, so we can use the method lm.confidence interval that will display the confidence interval like this. Okay, so now we get the confidence interval for intercept as well as t. Okay, this is the minimum confidence interval, this is the maximum confidence interval. Okay, simple. Okay, so now what we can do basically, we know the minimum and maximum value, right? We know the minimum and maximum value. This is the minimum and maximum value. We can compare with that, whether that coefficients are lying within this coefficients. Okay, so this is basically a 95% of the coefficients. Okay, so or we can most probably say that this is the first value, this is the second value. Okay, and if our coefficients are within this, then we can say that it is 95% confidence interval. Okay, there's one mathematical functions anyway, but nowadays, anyway, during practical session we are not going to use this because I never use this. Okay, so but if you have a chance, if you have a requirement to use this kind of things, basically you can use that. Okay, so now let us talk about one more thing. Okay, so now assume that I have more and more features. Okay, so last time, okay, we have seen only one features and only one target. We call it a simple linear regression. Okay, if the number of features is one, then that is called simple linear regression. But if the number of features is more than one, then it is called multiple linear regression. Okay, so now we have multiple linear regression, x1, x2, x3, x4, x5. Then the hypothesis function is x1 into w1 plus x2 into w2 plus x3 into w3 plus x4 into w4 plus x5 into w5 plus b. Okay, now we have to rewrite the hypothesis function like that because we have multiple input variables. So for x1 we have 1 coefficients, 2 coefficients, 3 coefficients, 4 coefficients, and 5 coefficients. Okay, so we have to calculate this 5 coefficients. Okay, so but and then we get some loss. Okay, the loss is 1.25. Okay, so now let us assume that. Okay, let us consider some examples. Okay, you have the input features. Okay, the number of experience, age, gender, name, marks, and then salary. Okay, this is the first feature. This number of experience is x1, this is x2, x3, x4, x5, and then what? Okay, let's think right now. Based on name, anyone can give the salary? Obviously no, right? So obviously what we can do, instead of keeping this variable, okay, we can remove this because based on name, no one is going to give the salary. Okay, so first of all, someone has to tell us, okay, whether this is important or not important. Okay, you can find by using coefficient value anyway. W1, W2, this is W2, this is W3, and this is W4, and this is W5, right? So for this value, I'll calculate coefficient, which is W1. For this value, for this variable, I'll calculate coefficients W2. Like that, I'll calculate 5 coefficients. Okay, this coefficient basically ranges from 0 to 1. Okay, 0 means nothing, means when when the W1 is 0, then there is no, means the y hat doesn't depend on x1 when the W1 is 0, means this x1 is not at all dependent with the y hat. So instead of keeping this, I can delete this. Okay, so that is W1 basically, but it is 1. Okay, when the x increases, then y also will increase. If it is -1, if the x1 increases, then the W1 negatively increases. Okay, so for example, if the W1 value is 0, okay, so no matter what the X value is, okay, if the W1 is 0, okay, whether the X increases or decreases, Y hat won't change at all. Okay, if the W1 is plus 1, then when the X1 value increases, same and equally Y hat value will increase. If the W1 value is minus 1, okay, let us put like this. If the W1 value is 0, okay, no matter what the X1 is, Y1 wouldn't change at all. Y hat Y hat won't change based on X1. Okay, so if the X1 changes when the W1 is 0, then Y hat won't change at all. Okay, if the Y1 is minus 1, then yes, if the X1 changes, okay, so assume that X1 value is 5000 and then W1 is minus 1. So X1 into W1 is minus 5000. So obviously the Y hat will decrease by minus 5000. So we have to see the coefficients, okay, that ranges from 0 to 1, and then we try to understand. From that we can understand that, okay, this value is important because the W1 is 1. This one is also important because it is 0.7. This is 0.3. This is 0. And this is 0.12 in that. But anyway, you cannot find coefficients as 0.1. It will have some coefficients, some random coefficients. Assume that 2. Okay, so you have W1, W2, W3, W4, and W5. Okay, so if someone tell us, so you can, from the coefficients, you can understand that which is important. Okay, number of experience is very, very important because the coefficient is set. The second important is age. The third important is gender. The fourth importance is mark. The fifth importance is name. Okay, now assume you have some 1000 number of inputs, x1, x2 till x1000. Okay, so then you have 1000 coefficients. Okay, so even though assume that the 500 values are 0.0002. Okay, even though it's a very small value, if 500 values has same kind of coefficients, obviously it will impact the output, right? But this is negligible, through that you cannot do anything at all. This is just a random coefficients. This is not real coefficients. So what we can do basically, we can come up with some technique. Okay, so we'll try to understand. Okay, if the coefficient is less than 0.005 for an example, or 0.05, okay, means if anything less than 0.05, otherwise you can think normal distributions. We mean to say it has to, the coefficient has to within the 95% confidence interval. Okay, so if it is out of the 95 confidence percentage interval, then we can remove that. Okay, so then someone has to tell us, okay, this is out of 0.05%, then we can neglect that. That is what we're going to do. Okay, so anyway, in the real time, if you see the real time example, you have so many input variables, 1000, 2000, or even 1 million. Okay, so then if your input is 1 million variables, if you have 1 million input variables, then you have 1 million coefficients. Okay, so obviously if you have 1 million coefficients, then obviously every small value will obviously impact your performances. Okay, so what we can rather do, we can neglect these features based on the confidence interval. That's what we're going to do. Okay, you got it right. So what we're going to do, we call it a p-value. Okay, that's nothing but the coefficients. Okay, okay, if the p-value is less than 0.50%, then we neglect that. Simple. Okay, so lm dot p-values, if the p-value is less than 0.05, then we neglect that. Okay, why we need p-values? You understand the concepts, right? So the p-value will tell us whether it is less than, means whether it is 5% confidence interval, 95% confidence interval. Okay, if you see the TV, okay, it is greater than 0.5. Okay, so if you see this is also greater than 0.5. Okay, so through that we can understand. Okay, so so what we try to do, okay, we calculate p-value. Okay, the p-value will tell us whether it is 95% confidence, means whether this is lying between the 95% or 5%. Simple. Okay, so right now, don't think that how I can calculate the p-value. We'll discuss that anyway. Okay, so right now just try to understand the essence of p-value. Okay, so when the p-value less than 0.05, it is 95%. When the p-value is greater than 0.05%, it is 5%. Okay, so this is what we're trying to do. So now we calculated p-value by using this function lm dot p-values. Okay, so now we got some two values. Anyway, we never care about intercept because intercept is not dependent with x1, right? Intercept, if you see the intercept formula, wx plus b, right? Intercept not depends with anything. Okay, so obviously we'll take only coefficients. Okay, let's take the coefficients for tv. This is less than 0.05, so then it is lying between 95% confidence interval. Yes, then there is a relationship between independent and independent variable, means there's a relationship between y and x. So we won't remove this coefficients, we'll need that. Okay, that's what we did here. And if a customer asked, okay, so he give from 5 variables. Okay, let us think. He give you have 3 input variables. Okay, so a customer asks, which is impacting my output, x1, x2, x3. Then what you can do, you already know the coefficients, w1, w2, w3. Okay, assume that w1 is 0.1, w2 is 0.3, and w3 is 0.9. Then you can say that this is the most important variable. Okay, whenever x3 changes, y changes by 0.9 times. Whenever x2 changes, y changes by 0.3 times. Whenever x1 changes, y changes only by 0.1 times. Then which is most important? This is x3. Okay, what some people will do, they'll eliminate this because why I need this 0.1%. I'll eliminate this, then I'll use only this, I'll fit a model. Okay, so through experience you'll learn all this, but through coefficients you can tell this whether I have a relationship between x and y, means independent and dependent variable. Okay. Okay, like that we're going to discuss a 3 more thing. Okay, so then we'll finish the session. Okay, the one is R square, adjusted R square, and then multicollinearity. Okay, so let's not worry about this. Okay, so we'll discuss. Okay, so now what are all the things we have did till now? Okay, so we'll come up with a hypothesis function. We'll come up with the last function, which is ordinary least square. Okay, so y minus y hat. For simplicity, I just write y minus y hat, but the real formula is different. Okay, so then what we did, we evaluate the model. How we evaluated? Through loss functions. Okay, then we try to understand the intercepts, coefficients, etc. Okay, then we'll try to understand whether these coefficients would come under the 95% of the confidence interval. So we calculate p-value. If the p-value is less than 0.05, it is very good. It is within the 95% confidence interval. If it is not, we'll remove that. Okay, that's what we have seen. Okay, so now how I can evaluate a model? Evaluate in the sense how I can make sure, how I can say that this model is good, this model is not good, something like that. Okay, so for that we have 3 things. Okay, so we have 2 things and we have something called multicollinearity. We'll see that. Okay, if the R value is 0 to 1, okay, R value generally is 0 to 1, okay, and then adjusted R square also, the extension version of R square, that is also 0 to 1. Okay, if the R square value is 0, then you can say that the accuracy is 0%. Okay, if the R square is 1, then the accuracy is 100%. Okay, so basically R square will tell us the accuracy range. Okay, so we have to find this. Okay, so what is the formula for R square? Okay, so there are two things. Sum of square are OLS residual, OLS average. Okay, what I mean by OLS residual? Okay, never confuse with that. Okay, so now we have some data points, right? Okay, if you take a straight line and then you try to understand the loss between the y hat and y value. Okay, okay, try to understand the loss between y minus y hat value, right? That is nothing but OLS residuals. Okay, like that. Okay, you'll take the OLS average, which is y minus y average. Okay, so what you'll do basically, you'll try. You already have some input, right? You'll try to find y minus y average. Means what is y hat value? Okay, so y hat is basically w x plus b, right? So y average is w x average plus b. So I'll take the average value of x, okay, and then try to predict y average. Simple. So now what I'll do, I'll just divide this. Okay, so OLS residual divided by OLS average. Simple. This is my R square. Okay, so 1 minus OLS residual by OLS average. So okay, so let us try to understand what is OLS average first of all. Okay, now you have this. Okay, x and y. So x is nothing but futures, y is nothing but targets. Okay, now you have so many data points in it. You have so many data points in it. Okay, for that you'll create a decision boundary. Okay, this is your decision boundary. Now what we're trying to do, we'll try to take all this value, average it, and then we'll come up with the average decision boundary. What I mean by average decision boundary? This is the average decision boundary. Okay, so means I'll take this value x1, x2, x3, and sum up with that, and then I'll come up with the average value. Okay, this is nothing but y average. Okay, this is nothing but y hat. Now what I'll try to do, I'll take the y average, I'll take the y hat, I'll take the y value, okay, and I'll try to calculate this thing. Okay, y less residual, y less average. Okay, then I come up with a formula like this: 1 minus y less residual divided by y less average. Okay, that will give me the value ranges from 0 to 1. Okay, assume that the y less residual is the actual losses. Okay, so for example, let's take an example. Okay, the x value is 1 and the y value is 1000, and then y hat value is 800, y average is 500. Okay, now let's replace this value with this formula. Okay, what is the y less average? Y minus y hat, which is 200. What is the, I'm sorry, y less residual, and y less average is 1000 minus 500, which is 500. Now, what is this? What is the 200 divided by 500? Okay, otherwise, let's replace this. 1 minus 200 divided by 500 is equal to 500 minus 200 divided by 500, which is 1 minus, so OLS average is y minus y hat, which is 200, divided by OLS residual is, means OLS average is 500. So I give 5.6. Okay, so 0.6 is okay as partial average. I get 60% of accuracy. So like that, based on R square value, you can calculate the accuracy. Okay, so if both are 500, okay, both are 500, they'll get 0. Okay, if this is 0, we'll get 1. Simple. Okay, if the y minus y hat is 0, we'll get 100% accuracy. Okay, if y hat and y average are equal, then you'll get 0% accuracy. Okay, so the point is, when compared to the average prediction, okay, we have to perform better, and then that measures the R square value. Simple. Okay, so R square basically ranges from 0 to 1. Okay, if it is more close to 1, more good. If it is more close to 0, it is not good. So that is what we try to define this. Okay, so adjusted R square, we'll discuss that in later section. Okay, because right now if I bring this equation, it will be more confusing. Okay, so we'll define only one thing, which is multicollinearity. We are not going to define the formula, but I'll tell you like what this concept means. Okay, so now let us start this fresh. Okay, okay, you have x1, x2, x3, and then you have y as well. Okay, so you'll calculate y hat. Okay, you'll calculate R square. Okay, you'll calculate all coefficients, and then b value. Okay, so using that, so these are all the things you calculated, and you have all this. Okay, so using R square, you can tell the accuracy. Okay, so using W1, W2, and W3, you can tell what is the relation between X and Y. Okay, you can tell all those things. But there's one more problem. Okay, let's define this. Okay, if the W1 is 0.05, okay, if the W2 was 0.5, okay, so through that, what you can understand. Okay, so if I increase the X value, okay, then the Y hat will decrease by 50%. If I decrease the X value, then the Y hat will increase by 50%. And what about Y2? If I increase the X value by 50, X2 value by 50%, then the W hat will also increase by 50%. If I decrease it, then it decreases it. So now just combine this. So I'll increase X1 by 50%. Okay, I'll increase X2 by 50%. What happens? Then Y value won't increase at all. Okay, so for example, let me try that. Okay, now assume that my X value is 10, X2 value is minus 10. Okay, so what is the Y value then? Okay, 10 into minus 0.5, which is minus 5, 0.5 into, I'm sorry, okay, I increase the X1 value by 10 and I increase the X2 value by 10, then basically 0. Minus 10 into minus 0.5 plus 10 into 0.5 will become 0. Okay, there will be no increase in W value. That's okay. Okay, now try to so this is one thing, right? This is one thing you have to define. Okay, now let us assume this scenario. I think you understand this, right? Okay, so how you'll get W1 value and W2 value, and when you increase the X1 value, how the W increases, means Y increases. When you increase the X2 value, how the Y hat increases. Okay, when you increase both values simultaneously, how the Y hat behaves basically. Okay, so it becomes 0 if you increase this value x as well as x2, x1 as well as x2. So can we say that there's a relationship exists between x1 and x2? Because when I increase x1 alone, the y hat increases. When I increases x2 alone, the y hat decreases. Okay, means vice versa. When I increase x1, y hat decreases. Okay, so when I increase x1, y hat decreases. When I increase x2, y hat increases. So then obviously there could be a possible relation between x1 and x2. Okay, that is not good for model because here both x1 and x2 increases. Okay, so obviously my y value should increase or decrease, but it becomes 0. Okay, so that's always a problem for me. So I have to make sure there is no dependency between x1 and x2. Okay, if there is a dependency, I have to reduce one by anything, anyone, because both are going to do same thing for my y hat. Okay, I have to decrease either one. Okay, so how I can find that? That is multicollinearity. Okay, we calculate something called variance inflation factor, just some value. Okay, if this value ranges from 0 to 1, if this value closer to 1, then there is a more chance of collinearity. If there's if the VAF value is close to 0, then there's a less chance of multicollinearity. Okay, so I'll calculate VAF value between x1 and x2, x1 and x3, x2 and x3. Okay, and then I'll try to understand which value I have to delete. Okay, so if I find multicollinearity between x1 and x2, I'll means x1 x3, I'll delete x3. I'll keep only x1 x2. That basically doesn't affect my performances. Okay, this is what multicollinearity. Okay. Okay, so you no need to remember all things. Okay, we have discussed so many things, but right now just remember this many things. Okay, so we have x1, x2, x3, and then we have y. We calculated xcat. Okay, how we calculated xcat? Because we know y1 means w1, w2, w3, and b. Okay, that's why we calculated y hat. Okay, after we calculated y hat, we come up with r2 square. That will tell us the accuracy. Okay, then we'll see, we'll take multicollinearity. Okay, so we'll try to understand the relationship between x1, x2, and x2, and x3, and x1, x3. Okay, if there's a more relationship between the independent variable, we'll remove that. And we calculate p-value. Okay, this will tell us whether the coefficients is between the 95% confidence intervals. If it is, I don't have any problem. If it is not, I'll delete that. Okay, so this is what we do. Okay, so first data collection. Okay, then I'll find model. Okay, then I'll fit the model. Then I will evaluate the model. Okay, so for example, how we can evaluate? For an example, I get R2 square as 0.6%, 60% of accuracy. Okay, my accuracy is very less. Then what I can do, I'll try to find the p-value for each and every variable. Okay, I've found that the x1 is not good. Okay, it is less than, means it is greater than 0.05, means it is 5% confidence interval. Then I can remove that. I'll keep only an x2, x2 and x3. Okay, and I'll try to calculate r square again. This time I'll get 0.8. Good accuracy. Okay, but still I can improve the accuracy. Then what I do, I'll take the multicollinearity. I found that there's a huge relationship between x2 and x3. So I'll try, means I'll delete x2 as well. I'll keep only x3. Then I'll calculate r square. It will give 100% accuracy this time. Simple. This is the evaluation process. Okay, I fit the model, I calculate r square. Then I'll use some techniques like multicollinearity, p-value, and I'll try to increase the accuracy. Simple. That is what we did here today. Okay, so maybe you can take this homework. So try to understand what hypothesis function is. Different loss functions. What is gradient descent and how it can be helpful. Okay, and then r square. R square we already discussed, and then try to see what is adjusted R square. Okay, why we need adjusted R square. Okay, try to understand the formula of multicollinearity. Okay, try to understand the formula of p-value. Okay, then practice everything in scikit-learn. Anyway, you already have this program. Okay, practice everything in scikit-learn. Then you'll come to a conclusion that this is how the linear regression works. Okay, plus if you want to, if you need a real-time experience, then you can go to Kaggle. Kaggle is a data science competition website. Okay, so you can find so many competitions here. Okay, they basically provides the data. Okay, they provides everything to you. Okay, so pick some competition. Okay, so I'll tell you one of the competition. Competition name is Zillow. Okay, this is Zillow's home value prediction. That's the competition name. Okay, Zillow's home value prediction. This is basically a regression problem. Okay, so go to Kaggle, Kaggle. Go to this Zillow home value predictions. Okay, just take this program. Okay, our program. Okay, so instead of our data, give the Zillow data. Okay, they provide some data, give that data and try to fit the model and try to understand the accuracy. Okay, come up with multicollinearity, come up with R square and adjusted R square, try to increase the accuracy. Just tell me how well you can able to do that. Okay, so if you need any help on that, I'll help. Okay, so if you go to Zillow's, you can basically download the data from here. Okay, training data. Okay, you can download that. Then you can basically, you can submit, and then you can estimate your accuracy. Okay, so that's how we can practice it. See, if you practice more, okay, it'll become better. Okay, so whether you understand the concept or not understand the concept, that's not very important, because I have a very good understanding on R square, but if I didn't walk for 1 year, I would have more chance to forget that. Okay, so until I practically explore. Okay, so what you can do basically. Okay, so take all the concepts what we discussed today. Okay, so try to understand that again. Okay, if you have any question, you have my phone number, you have my mobile number, you can call me at any point of time. I'm ready to help you. Okay, and then go to Kaggle Zillow home price predictions problem. Take the data, try to apply it by using the same program. This program is available in Acadgild. Okay, machine learning 2 examples. Take the same program, don't change anything. Okay, just change the data accordingly, and then try to predict. Okay, so okay, that's all about linear regressions. Okay, so it might be it might be huge to you. We may have so many parameters. Okay, but let's not worry about it. Okay, so okay, this is the concept we are going to discuss for the later sections. Okay, so next week we are going to discuss logistic regressions, right? In logistic regression also the same concept is going to follow. Okay, so never worried about it. Okay, so we're going to discuss, we are going to discuss multicollinearity, p-value again next week. Okay, so if you have a partial understanding this week, not a problem. Tomorrow we'll discuss the same thing. You'll have a complete understanding. Okay, so let's not worry about it. There's not an easy concept, but at the same time, there's not very difficult to understand. Okay, thanks for everyone. Thanks for participating. Bye.
Acadgild. Average is dead.